Okay, I think I need to a little bit go back and look on what we have done, at least at the end here. We have now the convergent. Okay. So every bounded monotonic sequence is convergent. Okay. Let me repeat that our quiz will be on Thursday. Okay. On Thursday, and today I will go finishing chapter 11. Hopefully, half of it we can finish by today. Let me check. Okay, I think we can move on to chapter 11.2. Okay. So Thursday, our quiz, chapter 10. Okay, let me start with the 11.2, which is the series. Okay. Okay, to illustrate what series means, let me just illustrate the Zeno paradox. Zeno paradox. Okay. So imagine you have conditions where you need to walk. Okay, you need to walk. You need to walk to the wall. So this is probably you, and then this is the wall. So you need to walk along the distance here. Let's say we have 1 meter, for example. But the Zeno paradox, they have rules, okay, that you can go along the distance half of the total distance that you already have. So for example, if you have this is 1 meter, you can go half. So the rest will be another half, right? But after you got half, when you walk again, you need to get by half again. So half becomes 1/4. Okay. So first, you're going to have half, maybe here. So this is half. Okay. And then you need to go half from the distance here, which means half for half is 1/4. Okay. And then the same thing, when you have this 1/4 left, you need to walk 1/8. So every time this man wants to go over to the wall, he needs to go by the half of the distance that's left. Okay. So imagine that if we imagine this is in a real situation, like maybe you can try like maybe 1 meter, it seems it's not really work out, because we imagine ourselves as a matter, right? As a matter that have mass, have a shape, right? But if we imagine the man is like a dot, like a point, with a single point. Can those points, or can the man as a point reach the wall? So that's the question. Can the point reach the wall? And in the real situations, it's impossible, right? It's impossible. So that's the paradox. That's the paradox. But if you try to compute tau plus 1 over 4 plus 1 over 8 and plus all the numbers that you can count close to this wall, it will getting numbers as close as much this one meter or just one. Okay. So we can imagine this in a terms that this man or this distance or this total distance can be expressed as the sum of infinitely many smaller distance. So half and we get that we have a pattern that this will going to work on 1 over 2 with power of n every time the man walks, right? And this will be getting closer to 1. The arguments for the paradox is it is not making sense to add number as many as infinite amounts, right? Because infinite is it's not an exact value. It's an abstract. Right? Infinite is abstract. But remember, like the situation we have pi. Okay. Pi is having infinitely amount of decimals. Okay? So if I write 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, and it still goes on, and I'm not sure how many, but yeah, infinite amount of decimals. This symbols or this pi we can also write in terms of sum. Right? So it's because we already know the definition that these numbers will be pi. If we add like more and more numbers, the total amount will be getting closer to the pi. So this gives idea or some conclusions that if we add these terms, so from this infinite sequence we can add, so if we add the terms of sequence an, we get this expression a1 plus a2 plus a3 plus a4 plus an plus, okay. We can also write in terms of sum or just the sigma and then an, it's also the same thing. let me move to the next page. So consider the Zeno paradox one more time, that we might have half 1 over 4, 1 over 8. Okay. If we add observe the partial sum. So this is half plus 1 over 4, it will be 3 over 4. So it will be half and then 3 over 4. This is the first term, only the first term. This is sum of the first two terms. And then another one is 7 over 8. It's 3 terms, okay? So first 3 terms. And then we can have more and more. Okay? And later you can verify that the n partial sum is, we can write in terms of this, or we can write 1 and then the sum, we can write this in terms 1 plus 1 over 4 plus 1 over 8 plus dot 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 plus dot 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 until infinite number. This will be equal 1. And we use similar idea. So similarly, consider as a partial sum, which consists of S1, S2, S3, and in general we will have Sn A1 plus A2 plus A3 plus dot 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 An is equal this partial sums getting a new sequence. So from this partial sums addition and adding terms, we can get a new sequence Sn, and if the limit exists, then we call it infinite series of the sequence. Maybe I will write in more official way. So let me take this into conclusions. So given the series let Sn denote its n partial sum, we can write the Sn in terms of the sequence itself It seems like confusing, but if you imagine like in the number, it makes sense. It makes sense. If the sequence convergent, then limit exists as real number. Okay, let me continue and copy this part. Let me just cut this and take it into new page. Okay. Okay. So if Sn convergent, then the series is called convergent, and we write A1 plus A2 plus A3 equal S, or we can write in terms of sum so the number S is called sum of the series. If the sequence divergent, then series is called divergent. Okay, let me make some notes here. So if this is convergent, this is exists. If this is divergent, this is series is diverge. So this is just to show that the partial sum has relations to the sequence or to the series itself. Okay. Okay, sorry. Okay, now suppose example, suppose the first n terms of the series is Sn equal to n divided by 3n plus 5. Then we can write the series is limit as n approaching infinity of the partial sum. Okay, of the partial sum. So we can just look at the partial sum and we solve the formulations by limit. Another important series or observations for series to find sum is, let me write here. Okay. So example, if we have sum 1 over n plus 1, okay. So we need to find this sum, or first we need to find whether it's converge or diverge, and then find the sum if it is converge. Okay. So first, we need to check the partial sum of the series. Okay. So let me add another variable I to take into our observations. And then we can see that this is going to be this pattern. Okay. So 1, 2, 2, 3, and 3, 4, up until we get n plus 1, right? We have this the partial sum. Okay. One way to observe this partial sum we can use partial fractions to look on the pattern. Okay, I hope you still remember the partial fractions. Okay. And then if we try to look at one more time using this already been decomposed by partial fractions, we can see our sum this becomes 1 over I and 1 over I plus 1. When we are start from 1, this will be 1 minus half. This is the first terms. Okay? The first terms. And then plus the second term, we add 2. Half minus 1 over 3. Okay? And then maybe we add more. The third one. And if you see, this is canceling nicely, right? And also 1 over 4 with another one, right? And you may write the conclusions that at the very end, at the very last term, we can write as simple as 1 over n minus 1 over n plus 1, but this will be canceling. Okay? And now we can have 1 minus 1 over n plus 1. This is for Sn. Okay? Then, finally, to get the idea clear from what we have before, we can take the limit. Okay, we can take the limit. So limit of Sn, this will be limit. This is 1. And we see that directly that this part here, this will be 1 over infinity, or it will be a 0. This will be 1 minus 0, or we can simply tell that the number is 1. Okay, if I try to take this into a graph, the sequence is going down. This is this sequence an. This is 0, right? This is n. And this is the value. And Sn is going here. Maybe here. This will be Sn. So notice that An is going to 0 and Sn is going to 1. An means the 1 over n plus 1. If you take the limit, it's going to be 0, right? If you take the limit as approaching infinity, it's going to be 0 for An. But for Sn, it's going to be equal 1, okay? So careful on maybe reading some text or some words or some questions, and you need to distinguish between the sequence and the series. The sequence is just a number. The series, you need to add the number. You need to add the number. Okay. We call this method also, this one here is called telescoping. We will maybe learn later about that. Okay. The next section is about the geometric series. Okay, I think you also have heard before, right? But what is geometric series and why it's called a geometric? So maybe we start from the definition that you might have heard before. So A plus AR plus AR squared plus AR cubed plus dot 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 plus AR and minus 1 plus dot dot dot, and this will result in sum from n equal 1 to infinity, AR, n minus 1, and A should not be 0. So the terms, they all having a common ratio with the R. So you multiply by R, by R, by R. Okay. We can also think the Zeno paradox from the previous one is also a geometric, with R is having equal half. Okay. Okay. Remember the Zeno paradox. This is A is half and R is half. If R is equal 1, then A plus A up until the end, it will be positive or negative infinity, right? And then it will be diverge. So if R is not equal 1, we have Sn the partial sum okay. This is the first equations. Secondly, let's multiply this Sn with R. Okay. So the R will be Rsn, this will be R, AR squared, AR cubed, and so on. Okay. And let's write at the bottom. Okay. So write that this will be R, Sn, and then we can write, let me write the first term here, AR squared, so that it is perfectly aligned with the first. Okay. AR squared, and then the last terms will be plus AR minus 1 and then plus ARN. Okay, because we multiply with R, we cancel it with -1, right? Okay. And then we subtract this to cancel the middle part. Okay. So we cancel all the middle part. Okay. So we subtract this. So this is 2. So 1 minus 2. This will be subtracting and canceling all the middle terms. So we will have Sn minus Rsn, right? And this will equal A minus AR to the power of n. Let's simplify and then let's factorize the Sn. So Sn will be A 1 minus R with power of n divided with 1 minus R. Okay. I think this is also you have maybe studied before. But if you forget how to get the formula, you can try to take the geometric pattern, try multiply by R, and then you subtract, and then you can develop the formula. Remember, the R with power of n is similar to what we have discussed before when we have the limit at this sequence. So we can take the interval. So if -1 less than R less than 1, so as n getting infinity, and the r with power of n will be getting 0. And then we know that limit so if this happens, then we can take this, okay? We can take this 0 for r with power of n. This will turns out to be a over 1 minus r. So as a conclusion, when r is less than 1, the absolute value r is less than 1, geometric series converges and the sum is a over 1 minus r. If r equal 1 or greater than 1, geometric series diverge. So for geometric series, the most important thing at the very beginning, when you know that the series is geometric, is finding the ratio. So when the ratio is on the interval of the convergence, you can find the value. But if not, then we can directly conclude that this will be divergent. Okay? But then, of course, how we observe the series from the pattern, that will determine how can you find the ratio. For example, okay, let me just wait for a few moments. And we can also apply this geometric with the Zeno that we previously discussed. So A will be half, R will be half, so 1 minus half. You can compute that, and then that will be the answer. You start with the A equals half. So it will be 1, right? It will be 1. So the Zeno paradox, at least we can approach those paradox through, at least for some of the geometric series. Some of the geometric series. Okay. Okay. Let's see if we can observe the series n equal 1. Whether this is converge or diverge. So because we now discussing the geometric, then the idea is how we can take this form and take this into the geometric. AR to the power of n. So let's try to make up those formulations. Okay. So in a series, because there will be so many tools or techniques that we might learn, it's important to distinguish each tool. So first is we can observe whether it's geometric or not. Maybe we can take the 2. We can write like that. And then maybe we can write 1 minus n and turns into n minus 1. Okay. Let's try that. So we take the negative. Right? Okay, and then I think we can write this in terms of 4 with power of n, and I will bring back 3 n minus 1 to the bottom. And then I would like to take this into the side. So 4 over 3 and minus 1. Or if you confuse, let me draw 4 multiply 4 and minus 1, right? Okay. So I can group these 4 and minus 1 with 3 and minus 1 become 4 over 3 and minus 1, and then it will be 4 for the number 3. Okay. And since we have this, we can imagine the geometric AR n minus 1. Okay, so we can see from this pattern that A will be 4 and R will be 4 over 3, and since R is greater than 1, then the series, so the sum is diverge. Okay. Okay, another example, or maybe another sections. Okay. Sum of the series of 1 over n. This will be 1 plus half plus 1 over 3 plus 1 over 4 plus dot 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 dot. Show the series diverge. Okay. I think we can have a short break. Okay, let's go back to this particular question that we need to show how the series diverge. We call this series also with the name of harmonic series. So whenever you find a series, it's always diverge. Okay, but how we can prove? Okay, there are several ways, but I think the most notable way, as you can also observe, is by checking the partial sum. So observe partial sum. I will begin checking the partial sums from the even partial sums, so S2, S4, S8, not even, but it will be having this S with 2 with power of n. Okay, so I will check at least these 3 partial sums, S2, S4, S8. If you want to get also S16, but I think I will just show you these 3 sum. Okay, so S2, as you might see from the series, it's just 1 plus half. Okay, just 1 plus half. Okay, and if we check S4, this will be 1 plus half, and then plus 1 over 3, plus 1 over 4. Okay, but what I would like you to observe is the last 2 terms. Okay, from here, if we exchange this 3 with 4, this will be half, right? This will be half. And this is still greater than 1 plus half plus 1 over 4 plus 1 over 4. Okay. So this is just to make the comparison easy. Okay. So let's make this 1 over 3 becomes 1 over 4. So we can now for sure the left part will be greater than the right part, right? Okay. And this is half, right? So we can write this is 1 plus 2 over 2. Okay. I will not write like the total is 2, just to show you the pattern. Just to show you the pattern. Okay. Now, looking at the S8, so we will have 1 plus half plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. Okay. Now the idea, this will be, I will do the same thing with the previous one. I will exchange this. And the rest, also similar with the previous one, I will exchange all the other numbers aside from 8, 5, 6, and 7, I will exchange them with 8. Okay? Just to make the numbers easily to be calculated. And from here, I can get the inequality that is 1 plus 3/2, right? 1/8, 1/8, 1/4, 1/4, 1/4 is half. Half and 1 is 3/2, right? Okay, so 1 plus 3/2. And if you get the 16, this will also give you at least 1 plus 4/2. So it goes by 1 plus 2/2, 1 plus 3/2, 1 plus 4/2, and so on and so forth. Okay. From here, at least we get the idea. In general, this will show you that the sum is always greater than 1 plus n/2. Okay, the sum itself is greater than this one, right? So it's greater than 1 plus n/2, which means that as the s to the power of n getting closer or approaching infinite number, then the n will also getting infinity. And so this series is divergent. So every harmonic series, like 1/n, when you see any problems or any questions that asks the harmonic series, it will always be divergent. It will be always a divergent series. Just if you want to make it maybe more clear, as 16, this will greater than 1 plus 4/2. As 32, this is greater than 1 plus 5/2. And as 64, greater than 1 plus 6/2, and so on and so forth. So this is the case for a harmonic series. Okay, now let's move a little bit. Any questions from this one? Any questions? You get the idea. Okay. If the series converge, then the limit of the sequence is 0. I think if we want to take some time to prove, we can. Okay? It's not too complicated. So let the Sn equal to the series A1 plus A2 plus A3 plus until some n, until an. Okay. We can write the an, the sequence an, as Sn minus Sn minus 1. Okay? An is the difference between these two partial sum, right? Okay. Now, and let the series of an convergent. So that the Sn, or the series or the sequence of the partial sum also converge. And then let the limit Sn approaching infinity of Sn is equal some number s. Okay. And then as n minus 1 approaching infinity, then should be n approaching infinity, then n minus 1 also approaching infinity. Then we also have limit of Sn minus 1 that is equal s. Also the same value as. And thus, as a conclusion, the limit of the sequence is equal with limit Sn minus Sn minus 1, or we can separate these two limits. This is, at the end, it will be s minus s, which is 0. Now from this proof, where we have a series, the series an, actually we have at least two components. The first component is Sn, a sequence of Sn. The second component is the sequence itself, the an, the sequence an, the an here. So we can write in terms of the series an, we have a sequence of the partial sum and sequence of this, the terms, okay, the sequence itself, the an, the original sequence. Okay, but remember, okay, this theorem, okay, we cannot reverse this theorem. For example, if the limit of the sequence is 0, then the series converges. It's not always true. But if we say the series of this AN converge, then it should be true that the limit of the sequence is 0. Okay. So we cannot reverse this theorem. Okay. So we need to make sure that the series need to be converged first. Then we are sure that the limit will be 0. Okay. What's the example for that? Let me just go back a little bit. This harmonic series, 1 over n, it's 0, right? But it's not converged. It's divergent. So we need to make sure it's converged, and then the limit is 0. Okay. It's also similar with the with this one. We know that this is converged, and the limit of the sequence 0. Okay. But from this theorem, actually we can reverse, but we say if limit of the sequence is not 0. So let me write, okay? If limit is not 0, or limit doesn't exist, then the series is diverge or divergent. For sure it will be divergent. So that's why careful to distinguish sequence and series. Okay. So when we have the series, we know the formula for the series. We take the limit, and if the limit it goes by not 0 or not exist, we can directly tell that this is divergent. So this is we call also test for or divergence test. Okay, divergence test. This is, I believe, one simple method to check whether the series is divergent or not. Okay. So whenever you find, oh, it's not 0, you can tell the series, oh, this is divergent. But if it is 0, you cannot conclude. You cannot conclude and think maybe you write converge. It's not always true, right? From the previous ones, we see that it's not always true when we have the limit 0. it's converged or diverged, it's not always true. We need to find another method if that's happening. So, for example, if you have if we check this series, we check the limit of the sequence and we know for sure that this will be equal 1/5, right? Which is not 0. So we say that the series diverge. Okay, some property of convergent series. Let me take this. So if series AN and series BN both converges, then if we multiply with a constant, it's still converge. If we add and subtract, it's also, we can do the property, all the property. So this is also converges. So what the property series means is A and Bn, it can be two different sequences. It can be two different sequences. So when we separate this, it's actually helping us to check each series. If one of them diverges, we don't need to calculate the other one, and we can just tell that the whole series will diverge because one of them is diverged. Okay? But if we get maybe this is converged and this is converged, then we can actually compute the number and the value. So today we have at least learned on the series, and then the sum of the geometric series, the divergence test, okay, and property of the convergence series. Okay, I think one more section for today and we can finish our class. Okay. So this is 11.2. I will move to 11.3, which is it's called the integral test and estimate of sum. Maybe let me just start with integral test first. Okay, first thing, we investigate the sum of 1 over n squared. Okay. If we take this expansion, this will be having, we can see that this is what it looks like, right? And I think we don't have any simple formula for the sum, for the Sn. But if we take some computer or using maybe calculator, the sum, it will be approaching 1.64 as the n approaching infinity. Okay. It looks like the series is convergent. Let's see if we can confirm the series by looking at the graph. Okay, let's say this is y equal 1 over x squared. Let's say this is 1, so if this is x and y. And this is 2 and 3, and we can look on, this will be the area. This is 1, right? 1 square area. This is the second one, 1 over 2 squared. So this is 1 over 1 squared. And we see that this will be 1 over 3 squared, and so on and so forth. And if we include these rectangles, it seems that we can also approach with the area under the curve as we learned in integral, right? So the sum of rectangles we can write in terms of 1 over 1 squared plus 1 over 2 squared, 1 over 3 squared 1 over plus dot 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 is equal sum. Okay. If we exclude the first terms because it's already established as 1, then the area, the total area under the curve for x greater equal 1, this is equal to this. Okay. Remember the improper integral when we have 1 over x and 1 over x squared. Right? 1 over x comes diverge when we have 1 to infinity, but 1 over x squared will be 1. Right? Will be 1. It's converged. So this is actually 1, okay, from improper integral. So the picture or the total curve, the area under the curve, so this shows that all partial sum are less than 1 over 1 squared plus and thus, okay, the partial sums we know it's bounded to this number, and also partial sums are increasing because all the terms are positive. So the series converge and the sum is less than 2, or we can write in terms of the series or sum this will be less than 2. Well, if we have time, maybe we can actually calculate what is the exact number here. Should be equal to pi squared over 6, or it's proven by the Euler. But let's just skip that because it's not in our section here. Okay, now another example, another case study is 1 over square root of n, or sum. Which is this is 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3 plus dot 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 dot. Okay. And if we imagine the same way we use the graph, and we imagine in an integral as area under the curve, we can imagine or compute the integrations of this improper integral from 1 to infinity 1 over square root of x. dx. And we know that because this is using the 1 over x to the power of half. This is less than 1. And we know that this will be diverged, right? Which will be diverged. This is from the improper integral. And this will be diverge. Doesn't exist or diverge. So the series is diverge. So by the end of the day, we can use our approach using integral to check whether the series is converged or diverged. But we need to make sure that this is the function need to be continuous. It should be decreasing. The function should be decreasing. And then we can take the integral and check whether it's converged or diverged. Okay. Let me write the conclusions at the new slide. So suppose f is a function, continuous function, continuous functions, positive, decreasing on so decreasing on 1 to infinity, because we will restrict our discussion only for the sequence and series, right? And let the sequence as a function of n, then the series convergent if and only if the integral, the improper integral, converge. In other words, if the integral converges, then the series converge. And if the integral diverge, then the series also divergent. And again, decreasing here, it doesn't mean that it's always decreasing. But in terms of interval, the majority will be decreasing. Okay. Maybe sometimes, maybe it's increasing a little bit and then decrease. Still okay. Because ultimately it will be decreased, or the majority of the interval is decreasing. So, to get you into the more idea on the chapter 11. So chapter 11 is actually, we are going to discuss about the sequence, the series, right? And we need to know whether it's converge or diverge from the series. And how we tell the series converge or diverge, there are several methods. So one method is divergence test, previously. Okay. So that's quite important, because mainly our goal will be determine whether the series is converge or diverge. So first is divergence test. Second one is the integral test. So each method may have pros and cons. Okay. It has a strength and weakness. Some sequence or some series, you can take the directly divergence test to check whether it's divergent or not. Some maybe you can check the integral test. Okay. There are other tests as well in the future, but at least I will just get you up until this integral test first. Okay. Okay, now as an example, test the series for converge or diverge. So firstly, what we're going to do is we need to check the functions. Let's just write with terms of x. So we need to check whether it's continuous. If we know it's continuous, and it should be positive functions, and it's always decreasing. So probably you can check first, and after you find that it's continuous, positive function, and decreasing, we can check through integral. And then we can solve by improper integral. If you still remember, we can use the limit to solve. This will be a tangent inverse. Okay, tangent inverse, it has negative, it has the infinite value, right? When it has pi over 2, if we imagine that in the first quadrant, this will be pi over 2 minus pi over 4, which equal pi over 4. So since converge, so the series also converge. And remember, pi over 4 is the result of the integral, not the result of the series. Different. Okay. But if we can find that the improper integral is converged, then we can conclude that it's converged. I think I will stop until here. Okay. So next Thursday, we may start the first hour with, I think we start with the quiz first, and then the next hour we can have the continuation of chapter 11. Okay. Because if I take the chapter 11 first, I believe you're still maybe preparing for your quiz, right? So I think we can start with the quiz first, and then the later part will be continuing the chapter 11. Okay. Okay, I think I'll stop here. So